Thank you. Now, with so many people being fair about sharing credit on their work today, I'm a little embarrassed about title page. Just see there, the work is based on my thesis, though, and my advisor played a big role in helping with that, especially we have a journal paper out of that, and he led the way in developing some of the fundamental results in here. Let's go ahead to contents. Now, where I'm starting from here is essentially a functional analysis question, but in solving it, it turned out that we could develop sort of a very streamlined way of describing it in terms of formal manipulation of symbols that takes us from functional analysis into a more combinatorial discrete math place. And over here, the first two parts are describing the functional analysis background, and the last part gets into this more combinatorial work. In these last parts, that's where the computation has come into play, especially there are experiments to work on a certain conjecture I had. But let's get started. From the top, we're interested in mixed norm spaces, so looking at what we call mixed Lebesgue norms. You may be familiar with the LP spaces, very standard sort of function space. Mixed norm spaces are like LP spaces, except whereas in LP you have, say, L1, L2, you have a single exponent. For mixed norms, you have a function of multiple variables, and with each variable you have associated different exponents. And here we have, let's say, a function in variables x1 to xn. You have different exponents, p1 to pn, and here we compute this p mixed norm of f by computing first the L1 norm in the variable x1, hold x2 to xn fixed, just work at one variable at a time. Do an L1 norm over x1, L2 over x2, so p2 over x2, up to finally pn over xn. And so this gives us more flexibility than standard LP. It allows us to consider functions that behave differently in different variables. You have, say, if one of the p is 2, you have square summability in one variable, or sorry, square integrability perhaps, or if you have L1 different one, just consider integrability in this other variable. So there's a definition, and you'll note also that since our computation depends only on the modulus of f, we can always assume our function is non-negative. So here's the sort of question we're looking at. Here's the simplest case, what I call the unpermuted case. Here you have, suppose you have two mixed norms that you describe by these uppercase p and uppercase q, which are these different, we have these different exponents, p1 to pn, q1 to qn. Also you notice that we can have different measures as well. We have the mu's, in x1 you have measure mu1, etc. And the p norm and the q norm you use these measures. Mu, the measures themselves play a role mostly important in terms of properties of the rounding in derivative. In practice, almost all the time there's a reduction to common measures. So when you take this problem and convert it into one where they don't play so important a role. The problem here is to find the best constant in an inequality. Here, if you look at taking the LQ norm and the LP norm, what's the least constant you can take for this inequality to satisfy? Now, and these mixed norm spaces are a certain class called function spaces. So this embedding when LP is contained in LQ is equivalent to having a finite best constant here. That's the norm of the embedding. Now, the important fact about this problem is that for such an inequality to exist, it's a necessary condition that you have one variable embedded. Because if you were to just take a function over x1, in order for this sort of inequality to hold the finite constant, you need to be able to take these LP1 norm and the LQ1 norm, have an inequality like this, but just in that one variable. So each variable, you need to have a classical LP inclusion. And the one variable question of when is LP contained in LQ is a solved problem. It has been known for over 20 years. There's a pretty nice write-up by Miami in the American Mathematical Monthly, for example, that describes conditions generally centering on features of
the Radon-Nikodym derivative between two measures is solved when you have inclusion in the one variable case. It's a necessary condition we will assume throughout that you always have one variable embeddings. Now, one feature you notice here is that you have these variables in the same order, x1 up to xn. Both of these, when variables occur in the same order, having one variable embeddings turns out also to be sufficient. So this is a very simple case, this unpermuted case. Now, so we're going to focus on something non-trivial. We're going to look at a permuted problem. We'll start with the two-variable case. It's, of course, beyond to solve one variable case, two variables is the simplest you can have. In two variables, there's really only one non-trivial permutation. So we have, say, like what we had before, we have P1 and P2 norms, Q1 and Q2 norms, these are different variables. And we call it a permuted problem because the P1 and P2, Q1 and Q2 are in opposite order here. And these are just convenient shorter forms to express what we could write in integrals as follows. And now, again, we can talk about corresponding one variable problems just in x1 or just in x2. And let ck, c1 and c2 give the best constants in the one variable problems. It turns out that here, the best c that you can get in the mixed one problem is always at least c1 times c2. So in order to get a finite constant in here, you need to have both those finite. But just having these one variable inclusions is not enough. We need something to get an inequality that goes from here to here. We need something to overcome this permutation, this different permutation. And Minkowski's integral inequality is a key ingredient. Here we have a somewhat generalized version of the standard Minkowski's integral inequality. If you have, suppose that you have a function of two variables, you have two signified measure spaces. And over here you have, you have exponents alpha and beta, beta greater than alpha. If you compute an L alpha norm inside in the variable x, and then an L beta norm in the variable y, that's what you have on the left-hand side here. It turns out that, and with the assumption that the outer norm, which is L beta, has a larger exponent, theta, that means then you have this inequality. It says if you reverse the order norms, if you take the bigger exponent, theta, to be inside, together with the y and its associated measure mu, then you get a bigger result. The standard Minkowski's integral inequality has 1 in place of alpha, p in place of beta, for a p greater than 1, but it turns out to be true for all kinds of exponents, alpha and beta. The gist of this is moving LP, single variable LP with bigger exponents inside, always gives you a bigger result. And the constant 1 here is the best constant. Oh, sorry, it says LQ there, that should be L beta, the notation used here. Note also, here, if the alpha and beta are the same, then these exponents in the middle, these ratios, are going to be 1, and what you have here is really just your Fubini's theorem, or Tonelli's theorem, technically. It's a version for non-negative functions. Now, so here's a solution to a large amount of the two-variable problem. As long as you have and here we are, again, I'm always going to assume you have one variable inclusion, you have finite constants C1 and C2. Now, if you have those, then to get a finite best constant in this two-variable problem, you have a sufficient condition here. If either of your P2 and Q2 are less than one of the P1 and Q1, then it turns out that you get this, as long as you also have one variable stuff. You get such an inclusion, and your best constant is exactly C1 and C2. There's a simpler special cases where this is in fact the entirety of your solution. So here we're talking about the variables live in sigma-finite measure spaces, which you can chop those up, and they have two kinds of pieces to them. They can be atomic, like the atoms. Think of sequence space, like counting measure. In any weighted counting measure, you have these individual points that have mass. Those are what we call atoms. A purely atomic measure is one where it's all supported just on atoms. Now here, we're interested in thinking, what if none of the measures you're working with are purely atomic? That means you have something other than just atoms. Think about integrals on the line, for example, or on an interval. So, if you, and there's, on an interval, we know the only barrier to integrability of a non-negative function is just as being too big. If a function is square integrable, so it's sort of the large values that will cause you trouble. The function is square integrable. Say the unit interval is integrable, and this sort of space. Now, an important thing about this, say here, this is the unit interval with Lebesgue measure, what we call atomless. Important thing is that you can take such a measure space, a unit interval, you can chop it up into really sets of very small positive measure. So as long as you have something like that, something analogous to the unit interval in there, something that works more like an integral than a sum, then this condition on the exponents turns out to be non-sufficient but necessary. And so here we have a full solution to that.
Excuse me. In the line below the display formula,
Yeah.
that's just saying that component-wise they must embed. Because it's sort of weird to see the CKs there when they don't come out in the final C.
Yes. Right. If this, say these are in each individual space. You have the single variable embedding. As long as you have both those and the relationship among these points, that's a full solution to the non-atomic case. That is, unless you have purely atomic measures, that is the whole thing. Now, when at least one measure is purely atomic, then we can also consider a non-Minkowski case. Like this. And let's see that. And the point of this, as it mentions at the bottom, as long as you don't have any atomic measures to worry about, as long as you don't have anything that works more like series and like traditional integrals, then you can make a counterexample. You can take little sets, make a counterexample. That's why it's a full solution. But when you have atomic measures, and some would counterintuitively think, okay, what's more complicated? Integration on the line or series or weighted series? Weighted series in a sense seem simpler, but they turn out in this case to be harder to deal with. When you have purely atomic measures, you also have to consider this non-Minkowski case. You might have inclusion, you might not have inclusion in that case. And if you have exactly one of the spaces, x2 and x1 being purely atomic, you get inclusion if and only if there's a certain power which the atoms have, the measures of atoms are p-summable somehow. Now if you have two purely atomic measures, there's a more complex situation. Then we have an answer that covers some known necessary conditions, some insufficient conditions, but there is a bit of a gap between them. So when I think about this, I think I wanted to get it, but it turns out to be hard. And one possibly heartening thing is you think, okay, P1, P2, Q1, and Q2, these exponents, if they were some randomly distributed four numbers, I could have 24 ways of ordering them. And this particular condition, where both the P1 and Q1 are less than both the P2 and Q2, out of, say, 24 orderings of these four things, there are only 4 of this kind. So in a sense, 5/6 of the cases are, you have inclusion, you have this sufficient condition here, Minkowski case, and fine. But if you have two purely atomic measures, things get complicated. And in particular, there's a case where there's a sort of challenging optimization problem that arises. It happens if your exponents are P1 less than Q1 less than Q2 less than P2, then you can reduce the functions of a particular form. And in these arises this generalized partition problem. In here, if you take, you have some exponent gamma between 0 and 1, take two non-negative sequences, and you can ask what would be the supernum of this expression where you're adding AIs each times a sum of BJs over sets J of I. So you take each index I with it, and you partition all the indices J. Imagine these indices, they can take, say, natural number values. Take the natural numbers, and so the indices in the sequence of these, partition those, and associate each set in the partition with one of the I's. The question is, how do you get the biggest value here? How do you best group the B's? And in this particular case, this computation should give you the best constant C, but it's a difficult one. And one thing to help reassure is that, although we don't have this fully solved, we made some observations on it. One thing to reassure is that, well, there are some fundamental difficulties observing that if you set things up right, you can get the optimizing partition problem out of these. If I takes on only two values, 1 and 2, then you're dividing the sequence B into different parts. And you get a maximum, and if you have equal weights A, you maximize by making the partition of the B's as nearly equal as possible. But of course, the optimizing partition problem is just one thing that can occur. There's, in general, rather more complexity in here. And this is the kind of computation that comes up in the hardest cases of the problem. So it's troublesome. Now, there's all those somewhat horrible complexities of the darkest parts of this problem. Let's try to come back to a way to describe some of the nicer, more pleasant features and look at how we can take some of this functional analysis concepts and encode them in a way that makes them amenable for computational experimentation, where we're thinking more combinatorially. So we look at what the two basic kinds of things that we do in a lot of the arguments that we use are using the one variable inclusion for the existence of these constants CK. And also using Minkowski's integral inequality, where it says you can reverse exponents to move the big one to the inside. You can encode these formally, and we can talk about a problem trying to seek an inequality. And we're trying to seek inequalities where I have this LQ on the left-hand side. Actually, if we go back, things like LQ stuff on the left, LP stuff on the right. And I can think of going from left to right in my inequality, trying to turn some starting permutation of symbols Q1 to Qn into P1 to Pn. The encoding we're doing is we can use a one variable inclusion. It's like turning a QK into a PK in your expression. We omit the constant CK just because with these operations, you always turn each QK into a PK. You get the constant you get turns out to be exactly the product, C1 times C2, etc. up to Cn. Especially because Minkowski integral inequality doesn't change the constant at all. There's a constant 1 in that. So we have these two steps we can do. We can turn a QK into a PK at any time, and we can exchange an adjacent pair. We can only do that if you make the big one to start the sequence. So we can look back at the unpermuted problem where you take a Q1 norm of Qn, want to turn it into P1 of Pn, and just use the one variable inclusions all in a row. Just turn each Q into a P. We can also prove the earlier described Minkowski criteria. If the P2s are smaller than the 2s are smaller than the 1s, this is sufficient for inclusion. And one nice thing here is that we can give a proof that really just is specified by these little sketches of transforming symbols. Here, if this criterion divides into several cases, and each of those you have an inequality between one of the two exponents and one of the one exponents. Our objective is to go from the sequence P2, Q1 to P1, P2. To do that, we need to swap at some point. What we do is we turn Q's into P's until we have exactly the two exponents mentioned in whichever case you're dealing with, Then we swap using the Minkowski step, and then you just finish turning them into p's. And now we look at, so that's how we get that Minkowski criterion, which solves a nonatomic two-variable problem. It turns out we can attack a lot of the multivariable problem too. What is a multivariable problem? You take in LP, LQ, and here instead of here we're looking at a permuted problem. The exponents Q and the associated spaces can be in any order. And again, we'll look for when is there a finite constant. Now, because there are difficult cases in two variables, it's at least as difficult in multivariable. There is good news though. As long, again, the simple solution is no measure is purely atomic. And now it turns out that for one thing, there's an argument we use to show that the one variable inclusions are necessary. We can get larger sort of subproblems. Say, for example, we start with, we're trying to prove an embedding that goes from Q1 to Q1, Q3 to Q1, Q2, Q3. So we're going to make a convention here that the Q's are permuted and we're trying to get them into P's in order. If you look at that Q2, Q1, Q3 start, you can just look at all these sub-inclusions here are obtained by just looking at all pairs of indices. You get Q2, Q1, Q1, Q3. You put them in the order they appear in here. Now, what we're going now these two variable sub-inclusions are always necessary conditions. So I think and in this way we reduce the multivariable problem to a two-variable problem. If we assume the two-variable problem, which we can, in the non-atomic case, handle, we assume all the two-variable stuff works. It turns out that's sufficient to get your multivariable work by, and we just do those sorts of manipulations. Over here we start with, say, for example, if you have a five-variable problem, you can do some transformations that take you from Q's to P's and sort them in order. And sorry, I misjudged time. Let me try to get to the part that involves conjecture that I can work on. Now, when you have non-atomic measures, two variable sub-inclusions are enough, as long as every pair, if you have every two variable sub-inclusion, it works. And I conjectured that if you have the same sort of inequality, that for permuted inclusions that you start with Q's are out of order, then if you get to assume that you have a certain inequality between Pj, Qj, and Pi, Qi, then you get the resulting that inequality, then that would be enough to get you a full inclusion. It seemed there's a certain condition you get for non-atomic measures, analogous to the L2, L1 thing, that P's are less than Q's that you don't have. I'm not assuming here. We can that I assume that I get a counterexample. Turns out that I haven't with the 6 variables programming, and in working on those, I found no counterexample, but certain see some insights into how the problem works. But that's all right. I think I'm out of time, so I will have to make way.